Flipped classroom video for further maths unit 2, continuous random variables. A random variable whose possible values cannot be listed individually is defined to be a continuous random variable. We restrict consideration to continuous random variables whose possible values are expressed as intervals between a and b, say. Then the probability density function f of x, which has got to be greater than 0 between a and b, and the total area underneath has got to add up to 1, and that is called the probability density function. And remember from histograms that it's the area under the curve which represents the probability. Therefore, for any possible value x of the distribution x, f of x is a measure of the probability in the vicinity of x. So if you have a point x here, then that is a measure of the probability that the area around x would be the probability in the vicinity of x. F of x is the upper boundary line of the histogram. And we can use greater, less than or equal here, as the data is continuous, so there's virtually no difference between using less than or equal. So that's the definition of a probability density function. If we wanted to work out the probability of x is less than the point D, which is within A and B, then we need to work out the area less than D but higher than A. So the area between A and D for the function f. If we want the probability between C and D, which is within A and B, then we need to integrate. So it's that area we need. We need to integrate the function. We need the area of the function below f of x between the points C and D. An example. The continuous random variable x is distributed with probability density function, that's the boundary function, f of x equals kx 4 minus x for 0, x between 0 and 4. Find the value of k, find the probability of x less than or equal to 3, and the probability of x greater than or equal to 2. Now, it's nice to think, what does the curve look like? So it's an upside down x squared k going through the points 0 and 4. So that's the area that's involved in this function. We know that the total probability will add up to 1. So if we integrate the function between 0 and 4, our total probability should become 1. Take the k out as it's a constant, and I want to integrate 4x minus x squared, which gives me 4x squared over 2 minus x cubed over 3, and I want that between 0 and 4. So I put the 4 in first and take away the value for 0. 4 in, I've got 4 times 4 squared divided by 2 gives me 32. 4 cubed divided by 3 gives me that. Put a 0 in and I get a 0. So the value of the bracket is 32 over 3. Take it over the other side, it becomes 3 over 32. So that's our value for k. Now we need to work out the probability that x is less than or equal to 3. I know my value of k, but I can leave it there for a minute. So I want to integrate less than or equal to 3. My lowest value is 0, so 0 to 3 is the area I want to evaluate, so up to the point 3 there. So I integrate, I get 4x squared over 2, x cubed over 3, I put my 3 in, and my 0 in becomes 0, I evaluate that, it comes to 27 over 32. So that's the probability up to the point 3. Greater than or equal to 2, well, greater than, I could integrate from 2 up until 4, but it's just as easy to say that it's 1 minus the probability up to the value 2. So if I integrate from, so I take 1 and then integrate from 0 to 2, work that out, take it away from 1, and I get the answer half. Obviously 2 is in the middle, but you don't know that always, so it's nice to check. Another example, now this function is given piecewise. It's this function up from 1 to 3, and then from 3 to 15, it's a different function. At the point 3, when x is 3 here, I do get 1 over 18. So they do touch at the point x is 3. So it's a continuous function. I need the probability that looks like this. So up until, so from there, the point 1 to 3, it looks like that. And from there on, it's 1 over 18, which is very small, but it's got a little bit of an area. So let's evaluate some of these. So between 2 and 3, I just use that function. So I integrate between 2 and 3, the first function, that's the same as x to the minus 2. Add 1 to the index, so x to the minus 1 over minus 1, which is the same as minus 1 over x. I want to put the values 3 in and 2 in. So I've got minus a third minus a half, which becomes a sixth. So that area between 2 and 3 becomes 1/12. Greater than 10, so 10 is here somewhere. Greater than 10, I want to integrate from 10 to 15. So I put, take the 1 over 18 out, and I put x instead, because I'm integrating a constant, I get x. Put the values 15 and 10 in, and I get 5 over 18 as the area. The probability of x is greater than 10. Between 2 and 6, now I need to do between 2 and 3, and then between 3 and 6, as I have two different functions. So between 2 and 3, I have, so I'm integrating, taking the 2 out, half out, I'm integrating 1 over x squared, which becomes minus 1 over x to the minus 1 over minus 1. My 1 over 18, take the 18 out, becomes an x. Integrating a 1 becomes an x. I put the values 3 and 2 into the first one. I'll take them away. I put the value 6 and 3 into the second one. And I get an answer which becomes a quarter. So 2 to 3, which I had originally anyway, I could have just put that in. And then from 3 to 6, I did the second equation. Less than 6, probability less than 6, so that's 6 down to 0. So I could do both again, from 3 to 6 and from 0 to 3, but it's just as easy to do 1, take away greater than 6. So greater than 6 is the second function. So I'm integrating the second function from 6 to 15. Take that answer away from 1, and I will have the less than 6. So I'm integrating that. I'm getting an x, as it's a constant. 15 in, 6 in, take them away, and I get a 9 over 18, which is a half, so 1 minus a half is a half. So less than or equal to 6, which is here somewhere, I've got a half as my probability. So that was the probability density function, which is the fx on the top. Now my cumulative distribution function is accumulating the probability up to a certain point. So for any random variable x, the function capital F now, such that f of x is the probability of the distribution x less than a certain point little x for all x. So the total of the probability up to a certain point, it's called a cumulative distribution function of x. You come across that in histograms. So consider a continuous random variable with possible values between a and b and probability density function f. Its cumulative distribution function is f and is defined to be below a there is no probability, so f of x is 0. So the cumulative distribution function is 0 below the first value. Between a and b is the integral up to a certain point of the function, and then above b it's the total probability, so it's equal to 1. Now the middle bit, we've got an x, because we need to integrate up to a point x, we need a different value for the variable inside the function. So we just change x to t. Sometimes they just leave it as x and up to a point x. It follows that f of a, so up to the point a is 0 and up to the point b is 1. Note that. So the integral of little f is our capital F. That follows that the differential of big F has got to bring us back to the probability density function. So the big F is the integral of little f, therefore little f must be the differential of big F. Another example, which is the same as the first one, but we are going to do the cumulative distribution function first. Okay, so there's our formula for the cumulative distribution function. We need to work out the middle bit. So between 0 and 4, I need to integrate between 0 and a point x, somewhere between 0 and 4. So I integrate, take the k out, I'm integrating 4t and then t squared. So 4t goes to t squared over 2 and t squared goes to t cubed over 3. I put my x in and my 0. X in brings the function to 2x squared plus x cubed over 3. 0 gives me 0. So that's my distribution function. I also know that at 4 it's equal to 1. So I can work out my k. I can put 4 in that function and I get that k is equal to 3 over 32. So my function, I need to write it out in full. So below 0 I got f of x is 0. Between 0 and 4 I've got this function with k being 3 over 32. So that's the value of the cumulative distribution function up to a point x, which is between 0 and 4. And then above 4, I've got 1. So that's the cumulative distribution function defined in full. Then we need to find the value of x up to a point 3. All I need to do now is put 3 in my capital F, put 3 in there because it's between 0 and 4, and I get the answer of 27 over 32 as before. My piecewise function as before, so I need to work out the cumulative distribution function of this. Remember, that's what I'm looking for. so between 1 and 3, being as I've got two functions, I need to do 2 bits. So between 1 and 3, I'm integrating from 1 to x. So I'm integrating, take the half out, t to the minus 2 becomes t to the minus 1 over minus 1. And that's the same as minus 1 over t. So put an x in, I got minus 1 over x. Put a 1 in, I got minus 1 over 1. So that becomes a plus 1. So plus 1 minus 1 over x is my function for capital F between 1 and 3. Between 3 and 15, I need, being as it's a cumulative distribution function, I need up to the point 3 and the integral then to a point x, which is between 3 and 15. So up to the point 3, I'm putting 3 into this function, and I need to integrate the second function. So the second function is a constant, so it's just t. I'm putting x and 3 into the second function. My first function becomes a third at the point 3, so it's a third plus the area above to a point x. So that is the cumulative distribution function when x is between 3 and 15. I'm adding my first total up to the end of the first, then the rest. So my definition of my cumulative distribution function for this combination would be naught for x below naught, that one between 1 and 3, and this one between 3 and 15, and above 15 I've got 1. So between 2 and 3 I need capital F of 3 minus capital F of 2, giving me, so they're both in the first one, so I'm using that function. So I'm putting 3 in the first one and then 2 in and taking them away, and I get a 12th. X greater than 10, so greater than 10, I've got to use my distribution function, my cumulative. So it's 1 minus up to 10. The capital F means up to the value 10. So put the 10 into the second function, and I get 1 minus 13 over 18, which becomes 5 over 18. Less than 6 is f of 6, which is in the second one, and it's up to the point 6. It's cumulative up to the point 6. So I'm getting that value for the probability up to the point 6. How to work out the median, the quartiles, and the percentiles. So for any value of p between 0 and 1, the value x of p, that value up to that point is the probability p, and that's called a percentile of the distribution. So the probability is p for a randomly observed value of x will be less than or equal to, so it's up to the value of that x corresponding to the p that we want. So suppose we want the median, so we want 50% of the probability, so I want x of 0.5. I want which x gives me 0.5 as my probability. The quartiles, the lower quartile would be 25% of the probability. So I'm looking at x, what x gives me probability up to 0.25, and the same for the distribution, upper quartile of the distribution. So f of x, the x giving me f of x to be 0.5 would be the median. The x giving me f of x being 0.25 would be the lower quartile, and f of 0.75 would be the upper quartile. So an example here, A continuous random variable has probability density function f, where f is 4 over 3x squared, and x is between 1 and 4. Find an expression for x be the 100th percentile of the distribution, and then find to correct to 2 decimal places the values of the median, the quartiles, and the 80th percentile. So I need to get a formula for the cumulative distribution function. So up to a point x, I can take the 4/3 out, and I just got 1 over t squared, which is t to the minus 2. So integrating t to the minus 2, I get t to the minus 1. Put the value x in and the value 1. That's the same as minus 1 over t. So I go minus 1 over x, and 1 in, I get a 1. So I can rewrite that as 1 minus 1 over x. So for a median, I need 0.5 as my, so it's the 50th percentile of that. So 0.5 probability would give me a value of x for the median. So I need, I put the cumulative distribution function equal to 0.5. I rearrange, I can take the 3 to multiply by 3 and divide by 4. I know I shouldn't be using fractions and decimals, but it works out okay in the end. So that gives me 5/8 as my 1 over x. So my x would be 8 over 5, which is 1 3/5. That's my median value. My lower quartile would give me a probability up to 0.25. So I need to work out what x gives me that. So I put my formula for the cumulative distribution function equal to 0.25. I rearrange, I bring the fraction over, and then I flip to get x instead of 1 over x, and I've got 16 over 3. Same for the third quartile, which gives me 3/4 of the probability. So I got 0.75 as my cumulative distribution function. I put them equal, multiply by 3, divide by 4, and I rearrange, and I get 1 over x to be 7 over 16. So my upper quartile is 16 over 7, which is 2 and a bit. And then the 80th percentile, well, I need now to put my f of x equal to 0.80. So 80 over 100 as the value of the cumulative distribution function. So multiply by 3, divide by 4, rearrange, 1 over x is 2/5, therefore x is 5 over 2. Working out the mean and the variance of a continuous random variable. Now, let h be a function of the continuous random variable having possible values between a and b, and the probability density function is f. An extension to the definition when x is discrete, the expected value is defined to be. Now this is for continuous and discrete. So the expected value of function of x means you multiply the function with your probability density function and integrate between the two values. So if we wanted the mean, we want e of x, so expected value of x now, giving us the mean. So I need to multiply x with my f of x and integrate between those two values. And I need to, then for the variance, I would need to work out e of x squared. So that would mean I multiply x squared with my function and integrate. Then the variance would be e of x squared minus e of x all squared. So this is for functions. Sometimes you're asked for expected value of 1 over x, so you multiply the 1 over x by the probability density function and integrate between A and B. An example, so we have a probability density function f of x equal to 6x 1 minus x, and it's between 0 and 1. So now upside down x crossing at 0 and 1, so that's the area we're interested in. We would need to find the mean and the variance, and then deduce the mean and the variance of a combination or a function of the x. So let's have a look. Mean and variance first. So mean, we need expected value of x. So I multiply x with f of x. So f of x was 6x minus 6x squared. So I need to multiply that with x and integrate between the two end values. So I'm integrating 6x squared minus 6x cubed, giving me 6x cubed over 3 minus 6x to the 4 over 4. Putting 1 and 0 in. So putting 1 in, I've got 6 over 3 minus 6 over 4. Putting 0, I've got a 0. So my mean is a half this time. So between 0 and 1, it's a symmetrical curve. My mean is in the middle as it happens. So we need the variance. So I need e of x squared. So I need to multiply x squared with the function. So the function would be 6x cubed minus 6x to the 4. Integrating that gives me 6x to the 4 over 4 minus 6x to the 5 over 5. And between 0 and 1, so I put a 1 in and a 0 in, and I get a 0, and my answer becomes 3/10 for e of x squared. Therefore the variance would be e of x squared minus e of x all squared. So I put my e of x squared in, and my e of x is a half, so square that, and I get 1/20 as the variance. So now part B, deduce the mean and the variance of this function. Now we did functions in the first video. So it's going to be that y now is 10x minus 3. So expected value of 10x minus 3 is 10 times the expected value of x minus 3, as it's a constant. So I can put the expected value of x in, work that out, and I get 2 as my mean of y. My variance of y, I can take the variance in, square the coefficient and ignore the second one. So it's 10 squared times the variance of x. Variance of x is 1 over 20. So I've got 5 as the variance of y. Y is a function of the continuous random variable x. Z is another function. So the mean of z is the expected value of this function. 2/5 is a constant, I can take it out. So then I've got the expected value of 3 minus x, which is 3 minus expected value of x. Take half as expected value of x, and I've got 3 minus a half, and then multiply by 2/3, and I get a 1 as the mean of z. The variance of z, I'll take the variance in, I square the coefficient, 4 over 25, then I have the variance of 3 minus x, take the variance in again, so it's, ignore the 3, minus becomes a plus, I'm squaring, and I've got the variance of x. So 4 over 25 times 1 over 20, and it cancels down to 1 over 125 as the variance of z. Another function, we need expected value of 5 x squared minus 3x plus 1. So taking e in, we've got 5 expected value of x squared minus 3 expected value of x plus 1. We worked out expected value of x squared in the last slide. It was 3/10. So I have 5 times 3/10 minus 3 times a half plus 1 works out to be 1. Now we need the mean and the variance of W, which is a half x now. So we need expected value of x to the power half. So that means I need to go back to the integration. I need to multiply by x to the half. So I've got x, 6x to the 3 over 2 minus 6x to the 5 over 2 to work out the integral. And then, so I've got add 1 to the index, so 6 to the 5 over 2 over 5 over 2, and 6 to x to the 7 over 2 over 7 over 2. Put a 1 in and tidy the fractions, and I get 24 over 35. The variance would be e of w squared minus e of w all squared. Well, e of w squared is just e of x. W squared would be x. So e of x minus e of w all squared would give me half minus 24 over 35 to the power half to the power 2, and that gives me 73 over 2,450. So different, little bit different here. And that is the end of the video on continuous random variables.